Namaste and hello and welcome to lecture number 2. So before we begin, I wanted to know if any of you had any questions, and if so, please raise your hand. We can quickly discuss. Yes, Deep, go ahead.
Yeah, I just wanted to confirm one thing from last class. So that example you had given where something's not a hypergraph or not a simplicial complex, right?
Yes.
So, for example, delta is 1, 1, 2, 1, 3, 1, 2, 3. That's not a hypergraph, and 1, 2, 3, 1, 2, 1, 3, 1, 2, 3 is a
Yeah. So
hypergraph.
let me just remember this 1, 1, 2. So maybe something like this, and this is example 1, and the second example is, let's say 1, 2, 3, 1, 2, 2, 3. Yes.
Yeah. So here, when I say vertices, I mean the zero-dimensional faces. So I collect all of them and call them the set V, right? In each case,
Yes,
that's how I.
that's correct.
So
That's right.
that's how I construct the V and the set E, and that's why one is hypergraph and other is not. I just wanted to confirm if that's
Yes,
the way
that
to
is
think
correct.
about it.
Yes, that
Okay.
is correct.
Okay. Thanks.
Okay.
Yeah.
All right. Okay. So are there any more questions? Yes, Rankit, go ahead.
So can you please discuss that convex hull example once more?
So I'll be talking about it, like I'll be repeating the discussion from last time's class. Maybe we can discuss it then. Is that fine? Okay. So my understanding is your question is, what do I mean by a convex hull? Is that the question?
Yes, and the representation you gave that
Yeah, yeah.
there
So
is
I
not
will
here.
discuss that today. Okay. All right. Okay. So all right. Okay, so let us begin today's discussion. Okay, so if you remember, last time we spoke about these two things, which is this notion of an abstract simplicial complex, and the other is a geometric realization. Okay, so as I mentioned, a simplicial complex is a generalization of a graph in that in addition to vertices and edges, it also has higher dimensional faces such as triangles, tetrahedrons, and so on. Okay, but there is another concept called as hypergraphs, which is also similar to which is also useful for representing higher dimensional faces. And the difference between a simplicial complex and a hypergraph is that a simplicial complex is required to be closed under the subset operation. Okay, so there is no such requirement for hypergraph. Okay, so that's the main difference. So in that sense, one can think of that every simplicial complex is a hypergraph, but not every hypergraph is a simplicial complex. All right. Okay, so thereafter we started discussing this idea of a geometric realization of a simplicial complex. Okay, so intuitively this specifies, okay, when I say geometric realization, I mean some sort of a recipe that tells us how to draw or imagine a simplicial complex, right? So some of you may be wondering, oh, what is so hard, and so on and so forth. Okay, so we will soon see why one needs to be careful about this. Okay, so more formally, by a geometric realization, I mean a way or an approach to associate a topological space to a simplicial complex. Okay, so one can immediately ask, oh, so what is a topological space? Well, a topological space is a pair. Okay, so pair which consists of x and tau, where x is some set and tau is a collection of subsets of this set x satisfying the following three axioms. The first is that in this collection, you should have the empty set and the whole set. This collection should be closed under finite intersections. And finally, we require that this collection also be closed under arbitrary unions. Okay, so if you have such a collection, then this set along with this collection is together forms what is called as a topological space. Is this okay? All right. Okay, so henceforth, okay, we will refer to the subsets of tau as open sets. Okay, subsets of tau as open sets. Okay, so one can ask, why do you need topological spaces and things like that? Well, the reason is that the main reason is you want to talk about continuity of functions that are defined over sets. Like, for example, your set could be the collection of all 256 cos 256 images, right? So if you want to talk of continuity of a function over this collection of 256 cos 256 images, right? So then one needs to know this concept of an open set, right? So without you being able to do that, right, you won't be able to talk about continuity of functions. Okay, so this is a topic for more suited to be discussed under functional analysis and some related topic. So I'll just leave this discussion over here, and we will continue to understanding this concept of a geometric realization. Okay, so again, the idea is I'm going to somehow specify a recipe, okay, that will tell us how to draw or imagine a simplicial complex. Okay, so let us say we have been given some simplicial complex delta, right, and we would like to draw this. Right. So the first step is we identify the vertex set of this simplicial complex, as one of you pointed out. Okay, this is the collection of all zero-dimensional faces in delta. Right. So in order to draw this simplicial complex, the first step is to identify or pick a function whose domain is V and whose codomain, or the set where it takes values in, okay, this is Rn. Right now, I am not going to specify what n you need to pick. Okay, so we will later on see what is a good choice for n. Right, so at this point we pick some f, okay, whose domain is V and the output is lies in Rn for some n. Okay, what n needs to be and so on and so forth. Okay, we will discuss later. Right, so what does this function do? If you give little v, okay, so little v is one element of this set capital V. Okay, so little v is one vertex. So if you give little v, this function f maps it to n-dimensional vector in Rn, and let's say x1, x2, all the way up till xn denote the different n coordinates of this vector. Right. So whatever function you pick, howsoever you pick it, I hope you agree that this function will induce the following functions. Right. So let me define what this function is. So for every d phase sigma, okay, so whenever I write d phase, I mean d-dimensional phase. Okay, and from the definition of dimension, I hope you are aware that a phase, if it is d-dimensional, it must have d plus 1 vertices. So accordingly, you can see that I have labeled the vertices starting from V0 all the way up till Vd. So you can see that there are d plus 1 vertices over here. Okay, so there are d plus 1 vertices over here. Okay, so actually I am having some trouble connecting to this Teams channel on a parallel device. So consequently, I won't be able to see any raised hands during the class. So if you have a question, please unmute yourself and directly ask your question. Okay, because I won't be able to see your hands if they are raised. All right, so let's continue. All right. Okay, so for every d-dimensional phase, this function induces the following function f sub sigma. Okay, so notice that I have used this notation f to denote that this is induced by this function f itself, right? And there is also a subscript sigma to indicate that this function is related or associated with this d phase sigma. Right, so this f sigma, notice, is slightly different than this function f. Right, the domain of this function was the vertex set, whereas the domain of this function is x raised to d. I will specify what x raised to d is. However, the codomain again is Rn. Whatever was Rn over here, okay, the same space you have here as well. Right, so first let me elaborate what xd is. Well, xd, okay, is the standard d simplex. Okay, so what is the standard d simplex? Well, it is the convex hull of these following points, right, in Rd plus 1. Right, so let's first count how many such points are there. Okay, so each of these vectors, okay, lie in Rd plus 1. So accordingly, this vector, okay, will have d plus 1 coordinates. Okay, so this will have d plus 1 coordinates, right? And notice that we are sort of moving the one, okay, sort of shifting it one place at a time. So you begin with one at the first place, one in the second place, all the way up to one in the last place. So I hope you agree that there are d plus 1 vectors over here. Is this okay? And you have to take these d plus 1 vectors and look at the convex hull of these points. Okay, so now let me elaborate what a convex hull means. Right? So if you are given a set S, then its convex hull is the smallest convex set containing S. Okay, so let me sort of first describe to you what a convex set is. Right? So very loosely, convex set means that if you have a set and if you take 2 points in that set, right, and let's look at the line connecting these 2 points. Right? So if this entire line lies within this set, then we will say this set is convex, right? So here is a quick example, right? So if I ask you whether this set is convex or not, the answer would be dependent on whether I can pick 2 arbitrary points and see if the line connecting these 2 points lies within the sets itself. Of course, for these 2 points, the line connecting them or the segment connecting them indeed lies within the set. However, if you carefully choose 2 points over here, say like this, and if you connect the points in this fashion, you can see that a part of the segment lies outside this set, right? So consequently, this set is not convex. Okay, not convex. Okay, on the other hand, this set is convex. Okay, so so in this way one can define a convex set. And what is a convex hull now? Well, if I give you a set S, this set can be arbitrary, then the convex hull or its convex hull is the smallest convex set containing S. Is this okay? So let me give you an example. Let's say I give you 1 point, right? So if I ask you whether is this set which only consists of 1 point, is it convex or not? Well, the answer is yes, indeed it is convex, because in order to verify if it is convex or not, we need 2 points, right? So here you don't even have 2 points, so you cannot construct lines in this fashion. Okay, so here the convexity condition is satisfied trivially, right? So so that's why this set which only consists of 1 point is convex itself, right? So the smallest convex set containing S, right? So S consists of only this point. So the smallest set containing S is S itself. Okay, so the convex hull of a single point is itself. On the other hand, let's say I give you 2 points and I ask you what is the convex hull of this. Okay, so let's label these points as V1 and V2, right? So let's label these points and let's say S is made up of V1 and V2, right? So and I can ask you what is the convex hull of S, right? So the first thing you have to ask is whether S itself is convex, right? It is not convex because if I draw a line connecting these 2 points, then this entire segment lies outside S, right? So S itself is not convex, right? So you can ask, okay, what if I connect these 2 points with this line and let's call this bigger set as, let's say, SH. Okay, so the H over here is used to represent hull, right? So is this a convex hull? Well, the first thing we have to ask is, does it contain S? So indeed it contains S. So notice that these 2 points lie in this set SH. Is it convex? So indeed it is convex, because if you take any 2 points in this set, if you take the line segment connecting these 2 points, I hope you agree that it lies within this set itself. Okay, so one can more rigorously argue it out that indeed the convex hull of 2 points is the line segment that is connecting them. So now one can ask, okay, what happens for 3 points, right? So if you look at 3 points, then indeed the convex hull would be in some sense the triangle which sort of joins them. Okay, so I don't want to spend too much time defining convex hull. Okay, for those who are not familiar, I encourage you to use Wikipedia or some other such resources, that and plenty of them are available, and you can read up about what convex hulls are all about, right? But nevertheless, let me talk about a special case. So let's say there are 3 points which are collinear. Now, if I ask you what the convex hull is, then the convex hull will just be the line joining them, right? So it depends on the position of the points, how the convex hull will eventually look like. Is this okay? So let me pause here for a second or two. If you have any quick questions in relation to convex hulls, convex sets, and related topics, let me know. Yes, Ramkit, go ahead.
So the function f and f sigma you defined above, are there some specific properties that they should satisfy?
We haven't discussed that. We will discuss that. Okay. So at this point, I have only talked about convex hull and convex sets, right? I will talk about what this. I have talked about the domain of f sigma, which is xd, right? Xd is supposed to be the convex hull of these points in Rd plus 1. So I hope that is clear. Is this okay? So so we will come to the definition of f sigma. We haven't discussed it yet. Okay. So are there any questions relation to convex hull and convex sets? Okay, so I don't see any raised hand, so maybe we can continue. Okay, so now, so recall what I said about xd plus 1, right? Xd. Xd is the standard D complex or the convex hull of these D plus 1 vectors in Rd plus 1. So let's try and understand what x0 is, right? So for x0, sorry, I have to write it in as a superscript. Okay, so this is incorrect. I should write it like a superscript, and I think I've made a mistake here as well. This also should be x2, right? So for x0, right? So x0, sorry, xd is the convex hull of points in Rd plus 1, right? So similarly, x0 is the convex hull of points in R, right? And in R, right, you have to look at these D plus 1 vectors. So D is 0. So 0 plus 1 is 1. So you only have to look at one vector. And what is that vector? You have to just look at one, right? So you take this point over here, right, and ask what its convex hull is. So as I said, right, for a single vertex, its convex hull is itself. So this is your x0, right? Now let's look at what is x1. So for x1, you have to go to R2 and look at these two vectors, that is 1 comma 0 and 0 comma 1, right? So I hope you agree that these are two vectors, right? And you have to look at the convex hull of these 2 points. So this is the vector over here, and this is the second vector over here, and you have to look at the convex hull. I hope you agree that the convex hull is the line segment that connects these two vertices. So this green part over here, okay, which includes these boundary vertices, together they form the standard one simplex, that is x1. Now if I ask you what is x2, for that you have to go to R3, look at these three vectors 1 0 0, 0 1 0 and 0 0 1, and look at their convex hull, right? So the convex hull will be the triangle that sort of connects them, right? And it will include the interior as well. Okay. So the convex hull is the smallest convex set that contains them. So I hope you agree that the convex hull is not just the boundary, right? It's not just the boundary, because if I take 2 points over here, right, and if I connect them, this portion will not lie within this set, right? So that's the reason you have to take this entire shaded region over here, and together this will form the standard 2 simplex. Is this okay? So I hope it is clear what xd in general means. Is this okay? All right. So with this, now let's try to understand what F sigma is, right? So let's try to understand what F sigma is. F sigma, okay, goes from xd to Rn. And as I specified, this Rn and this Rn must be the same, right? So how is F sigma defined, right? So xd is basically a convex set. So you take an element of xd. So recall that xd is a subset of Rd plus 1. So any element of xd, one should be able to represent using d plus 1 coordinates, and these are the d plus 1 coordinates. Okay, so I have denoted them by lambda 0, lambda 1, all the way up till lambda d. Okay, so this is an element of xd. You take such an element, right, and define it to be this function over here. Okay, so this is the definition. Okay, so a point about notation: whenever I write a equal to with these two dots over here, okay, so that means I am defining it. Okay, so this is definition, and the position of the dots, okay, indicates which term is being defined. position of dots indicate which term is being defined. Okay, so because these dots are on the left, it means that this expression is being defined. Okay, so f sigma of lambda 0 all the way up till lambda t, this is defined to be lambda 0 times f of v0, right, plus dot 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 lambda t times f of vd, right? So notice that the expression of the in the right is made up of these lambda 0 to lambda t, which are an element or the input from xd that is given to f sigma, right? And sigma, recall, is made up of these d vertices, d plus 1 vertices. And recall, this function f over here associates to every vertex v an element in Rn, right? So this is a real value. This is multiplied to a vector in Rn plus 1. So this entire thing will be a element in, not Rn plus 1, but rather Rn. So this is a real number. Okay, this belongs to Rn. So together this belongs to Rn, and similarly this belongs to Rn, and you are adding vectors in Rn, and together this entire expression will be an element in Rn, right? So you can see that using the function f over here and the input that we give to f sigma, one can construct an element of Rn. Okay, so that's why I say this f induces this map f sigma. Is this okay? So whatever you choose f, one can accordingly define f sigma in the following fashion. Is this okay? So let me pause here for a couple of seconds. If there are any questions with regards to the way we have defined f sigma, this may be a good place to ask.
Hello, sir.
Mm-hmm.
Sir, f of v0 and up to f of vd are the vectors, right?
Yes. Yes.
And lambda 0 into f of v0, those terms are the scalar multiplication, right?
Scalar multiplication of a vector in Rn. That's correct? Okay.
Okay, yeah.
All right. Are there any more questions? Okay. So yes, Jacob, go ahead.
Any conditions needed on lambdas, like they should sum up to something, or
so the constraint is that this lambda 0 to lambda d, they have to lie in xd. That is the constraint. So that will automatically imply, okay, so if you think about this xd a little bit, that will automatically imply that these lambda 0 to lambda d all should be numbers between 0 and 1. And furthermore, these lambda i's, I equals 0 to d, they have to sum up to 1. Okay, so this two conditions follow from the fact that this lambda 0 to lambda d, this vector lies in xd. Is this okay?
yes.
Okay, so that condition automatically implies these additional or this subsequent conditions on these coordinates lambda 0 to lambda d. All right. So now what we have understood so far, okay, so suppose you come up with a function f which goes from v to Rn, right? Now every such function, howsoever you come up with this function, so far I haven't told you how to come up with this function, but howsoever you come up with this function, right, every such function will induce this f sigma for all sigma in delta, right? So delta is a collection of subsets of this vertex set v, right? So you pick one such subset. Now for every such subset, you have this function f sigma defined as we did above, right? Now suppose the following two conditions are true, that is f sigma is injective, right? So injective means that it is 1-to-1, right? So suppose this function f sigma is injective for every sigma in delta, and furthermore, suppose the following condition holds. So let me first read it and then I'll explain it. Okay, so on the left hand side, you have image of f sigma intersection with image of f tau. This intersection must equal the image of f sigma intersection tau. Okay, and this should hold true for all sigma comma tau in delta. Okay, And we can also emphasize that sigma is not equal to tau, because otherwise this condition will be trivially true. Okay, so the first thing we have to understand is what is this Im over here. Well, the Im denotes the image of this function. Okay, so this is so let me just specify. So Im of a function, a generic function. Okay, so let's say you have a function g that goes from x to y, right? And image of g is basically all y in capital Y, such that there exists some x in capital X, such that f of x equals y. Okay, so this is what image of g means. Okay, pictorially what it means is that, let's say this is x and this is y. So let's say there are a bunch of points here, there are a bunch of points here. Okay, so let's say this element over here gets mapped over here, this element gets mapped over here, this element gets mapped over here, this element gets mapped over here, and maybe this element gets mapped over here. So you can see that some elements get left out, right? Because there is no element in X which gets mapped to these elements. So if I ask you what is the image of G, well, your answer will be the bunch of these points over here. Okay, so that's formally what is written over here, right? So if these two conditions are satisfied, that is f sigma is injective for all sigma in delta. Furthermore, if image of f sigma intersection with image of f tau, if this intersection equals the image of f sigma intersection tau. So notice that sigma is a subset of the vertex set. Tau is also a subset of the vertex set. So sigma intersection tau will be another subset of the vertex set, right? So since delta is closed under the subset operation, sigma intersection tau will also lie in delta, right? So this is another phase, right? So associated to this phase also, so let's call this as sigma prime, right? So associated with this phase also, there will be a function which is f sigma prime, and we require that this condition over here be satisfied for every sigma and tau, such that they are not one and the same. Is this okay? If these two conditions are satisfied, okay, then if you take the union of images of f sigma over sigma in delta, this union we will represent by this notation over here. This along with a bunch of sets we will refer to as open sets is indeed the geometric realization of delta, right? So now let me the last thing I need to explain is what are these open sets over here, right? So first, let's try to understand what this is, and we will try to understand this via some examples. Okay, so mathematically, while this is very compact, it may be sort of an overload to understand in the first instance. So we will look at a bunch of examples, try to understand what this is, and then we will eventually try to understand, okay, how do we define the collection of subsets of this set, which we will refer to as open sets. Okay, so let's look at a bunch of examples, okay, as to how to construct this geometric realization. Okay, so in these examples, we will keep things extremely simple, right? So there will be no complication. So let's try to understand. Okay, so we have been first given a simplicial complex. Okay, so it includes these vertices 1, 2, and then in addition to these vertices, we also have this face with two vertices, which is 1, 2, right? So as I mentioned before, okay, this is a sloppy or a lazy way of writing, but nevertheless, we are using this convention for convenience. Okay, whenever I write 1, 2, it is supposed to be interpreted as the set that includes the two elements 1 and 2. Similarly, this has to be interpreted as the set that contains 1, and similarly this needs to be interpreted as a set that contains only the element 2. So in this way you can see that delta is a collection of subsets which satisfy the property that they are closed under the subset operation. Is this okay? But this is just a sloppy way of writing, but this is not the element 1. Instead you should think of this as the set that consists of the element 1. Similarly, this should not be interpreted as the element 2, but this should be interpreted as the set that consists of the element 2. Is this okay? All right. So given this delta, right, we can construct the vertex set. So this consists of the two vertices 1 and 2. right? And the first thing, right? So before we look at the geometric realization using the recipe that we discussed above, let's first try to intuitively understand how would I go about drawing this simplicial complex, right? So you may think, oh, this is 1, this is 2, and this is the edge that connects between them, right? So so you can ask, oh, what is so hard in visualizing this simplicial complex over here, right? This is the way that one should visualize this simplicial complex. Well, the answer to your question is indeed this is how one should visualize this. And what we will now do is we will go over the recipe and see if we indeed get some drawing which looks like this. Okay, so that's our goal, right? So on the other hand, let me also tell you why this recipe is useful. While for such a simplicial complex, it was easy to say that, oh, it can be drawn like this. But imagine if you have a simplicial complex which has, let's say a billion vertices and, several edges, and similarly several triangles, several higher order faces, and so on and so forth. Okay, how to draw it? Right, so if you draw it in, let's say, a million dimensional space, so you have billion vertices, but let's say you try to draw it in a million dimensional space, would you encounter some issues, and so on and so forth? So those are the kind of questions, okay, that this geometric realization will help us try and resolve. Is this okay? Or try and answer. So before we sort of venture into all those questions, let's try to look at this simple example and see if its geometric realization indeed looks something like this. Okay. Okay, so the first thing we have to do is we have to look at the vertex set of this simplicial complex. So this includes the two vertices 1 and 2, right? And we have to somehow identify a function, right, which goes from V to some Rn. And here for simplicity, let's take a function which goes from V to R, right? So there are two vertices. So this function I have to define on what happens when I give 1 as the input. So this is the first vertex over here, and what happens when I give the second vertex as input. Okay, so for the first vertex, I am associating the number 5, and for the second vertex, I am associating the number 10. Is this okay? Now, why did I assign 5? Why did I assign 10? Well, these are arbitrary choices. The key thing to keep in mind is that these are real numbers, and importantly, these two real numbers are distinct. You could have as well chosen minus 150 and pi over here. Okay, nobody would have cared, and the analysis wouldn't have differed in any way. But the key thing is these two are real numbers, and these two numbers are also different. Is this okay? So now let's see how does this function f induce these different nf sigmas over here. Okay, so the first thing, notice that this simplicial complex includes three faces, right? So 1, 2, and 1, 2. Okay, so we have to identify what is f1, we have to identify what is f2, and we have to identify what is f12. Right? So what is f1? Well, since this is a zero dimensional face, right? F1 will go from x0 to R. Is this okay? And recall from our earlier discussion that x0, okay, only consists of this single point over here, which is 1. Right? So we have to basically define this function only for this input over here. Right? So how did we define? So recall the definition: f sigma of lambda 0 all the way up till lambda d is lambda 0 of f of v0 blah 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 all the way up till lambda d of f of vd. Right? So in this case, this collection is only made up of 1. Right? So this is a one-dimensional vector, and the only vector that is there in x0 is the vector 1. Right? So this is 1 over here. So if I give 1 as input to f1, this should be, okay, so f sigma of lambda should be lambda times f of v, right? Since sigma only consists of this single vertex v, right? So that is what I have done over here. So notice that this is the 1 and this is this f of 1, since this face over here only includes this vertex. So 1 times f of 1. So since this is 5, this entire expression will evaluate to 5. So you can see that I have completely defined this function f sub 1. Is this okay? So let me pause here for a second or two. If there are any questions with regards to how we defined f sub 1, please let me know. Once you understand this, the rest of them is similar. Okay, so if you have any questions on how we defined f sub 1, please let me know. Yes, Jacob, go ahead.
If there are more points, then lambda can be anything, right?
I mean, anything meaning it should be element of XD, right? So since the face that we are considering is the set that only includes vertex 1, right? F sigma, the domain of this F sigma should be X0. However, if the face consists of more than 1 point, then the domain has to be XD. Is this okay?
Yes, sir.
Okay. Okay, so I don't see any more raised hands, so maybe we continue. Okay, so in the same way, Pankaj, you had a question?
Good morning.
Yeah, please go ahead.
Why the function f is from v to r, not r2 or something?
Yeah, so this is right now a choice we are making. Whether it works or not, we will verify later. If it works, well and good. If it doesn't work, we will change this r. Is this okay? Right,
Okay.
at this point, the choice of r is trial and error. Okay, so I will say this is a trial and error. Okay, this is just to understand what is happening and so on and so forth. I have not made any conscious decision that it should be r1 only. I have chosen it arbitrarily for the time being. All right. Any other question? Okay. Yes, Siddharth, you had a question. Siddharth, please unmute.
Am I audible now?
Yes, you are audible.
Good morning, Gugan. I
Yeah.
was just wondering whether this set we are generating is the same as akin to the generating set in linear algebra.
Which set are we generating? Which set do you mean?
The sigma, which it is the uh, the primary, the basic generating set we had, having ones each time for different dimensions.
I don't know what you mean by generating set. So we had a concept of a basis in linear algebra, right? I don't know what do you mean by generating set. Like, I don't know, in the context of this set of polynomials, we had this zero-dimensional polynomial, one-dimensional polynomial, or degree 1 polynomial, sorry, degree 2 polynomial. Is that what you mean by generating set?
Yes, the basis where we took a general basis wherein for every this thing dimensional we took.
So here
one.
notice that we are not trying to construct a vector space or things like that. Here we are trying to draw things. Okay, so in a sense, you know, these so here we are not trying to construct a vector space. Instead, we are trying to construct a topological space, right? So a topological space and a vector space are two different entities, right? I mean, these things will appear similar, but you have to keep in mind the properties that we are interested in. Is this okay? When we are constructing a vector space, there is a certain set of properties that we would be interested in. When we are trying to construct a topological space, there are a different bunch of properties that we would be interested in. So when we try to construct things, it may appear similar, but we have to be careful what properties are being studied over here. Is this okay? So you just don't have to look at the symbols and notations. Oh, there also I had F1, here also I have F1. Okay, so are we doing something similar? So the short answer is no. It's because here we are trying to construct a topological space. There we were trying to construct a vector space. Is this okay?
Understood, sir. There is no relation whatsoever between the two.
Because here we are not talking about vector spaces and things like that at this point. Later on, we will again come up with vector spaces. Is this okay? Right.
Right.
So, so at that time, we will see how we construct these vector spaces. But right now, the goal is given a simplicial complex, how to draw it. Right. That's what we are trying to do.
Right.
Okay.
Thank
Now, so this is how I constructed this F1. Similarly, F2. So recall when I write F2, I ideally should write it in this fashion so that this makes it explicit that this function over here is associated with this set which consists of just the element 2, right? But nevertheless, I'll be a bit sloppy, and I will trust your understanding of this subject, so that you will be able to decipher, right? When I write f2, I actually mean something like this. Okay, so again, since this set over here includes only one element, okay, the domain of this function will again be x0, and the codomain will be R, which is the codomain that we chose for f, right? So this has to be the same once we fix this codomain over here. Again, since this only includes the element 1, we just have to define f2 for this particular entry, and by using this definition again, you can see that this will be 1 into f of 2, and since f of 2 is 10, I hope you agree that this entire expression will be 10. Right? So f1 I have completely defined. I have defined f2 completely. Okay, this is I purposely chose these simple examples so that you have first gain some foothold in in trying to figure out what we are exactly trying to do. Okay, and then you will be able to construct these complicated examples, which I will ask you as part of some exercise, or it could either be part of some assignment or midterm exam. All right. So the final thing we have to construct is this f12 over here, right? So notice that this face over here includes two elements. That's why the domain of this must be x1, right? So x1 and the codomain must again be R, which is the same over here, right? So this is defined in the following way. For lambda 0, lambda 1, which lies in x1, the output, so give me any lambda 0, lambda 1, the output will be lambda 0 times f of 1 plus lambda times f of 2, right? So let's try to recall what is happening over here, right? So recall, this is your x1. This is the line segment that connects these two vertices over here. So this is your x1, right? And your f12 function takes x1 and maps it to R. Is this okay? So this is what is happening. So you give me any element over here, right? And this f12 function will map it correspondingly to some number in the real line. Okay, so let's try to investigate this a bit more, right? So since lambda 0, lambda 1 lie in x1, okay, this automatically implies that lambda 0, lambda 1 should be numbers in 0, and should be numbers that lie in the interval 0, 1. And furthermore, they should satisfy the property that lambda 0 plus lambda 1 must be 1, right? So this, I hope you agree, is the equation of this line segment over here. Is this okay? So now I hope you agree that 0, 1, okay, this lies in x1, right? So 0, 1 is precisely this element over here. Similarly, I hope you agree that 1, 0 also lies in x1. Right, so now let's try to see where is 0, 1 and 1, 0. Where do these two vectors get mapped to? Right, so f12 of 1, 0 is precisely 1 times f of this one, okay, plus 0 times f of 2, right, which is the second element, second vertex in this face over here. So this is precisely f of 1. So I hope you agree that this is 5. Right, so what we have managed to show is that this vector over here gets mapped to 5. Okay, now similarly, let's try to understand what f01 is. So this is 0 times f of 1 plus 1 times f of 2. So I hope you agree that this will be 0 plus this part will be 1 times 10. So this is 10. So what we have managed to figure out is that this element over here gets mapped to this 10 over here. Now let's see something like f half comma half, right? So I hope you agree that half comma half will be somewhere over here, right? So this half comma half will be this would be half of f of 1 plus half of f of 2. So this will be 5 plus 10 over 2, which will be 7.5. So you can see that this element over here will get mapped to the midpoint, which is 7.5. So in this way, you can see that every element over here will get mapped to suitable elements on this real line between 5 and 10. Is this okay? So now with this, we have finished constructing, f1, f2, f12. right? Now what remains remains to do is verify the two conditions that we had mentioned, so that we can verify if with this function f can we come up with a geometric realization of delta, right? So the first thing we have to ask is whether these three functions are injective or not, right? So f1, okay, maps 1 to 5, right? F2 on the other hand maps 2 to 10, right? So you can see that there is just one element in the domain of f1. Similarly, there is only, sorry, f2 maps 1 to 10, sorry about that. So in the domain of f1 and f2 there is just one element, right? So there is the question of whether these functions are injective or not, that is very trivial, right? So they are indeed injective. Similarly, if you look at this f12 function, right, this is injective because every element on this set is mapped to an unique element on this set over here, okay, or this region over here. That's why f12 is also injective, right? So in this way we have trivially verified that f1, f2 and f12 are all injective functions. And now what remains to check if is that whether these images satisfy the desired property, right? So recall, we need to verify that image of f sigma intersection image of f tau equals image of f sigma intersection tau. Okay, so first let's try to what should I say? Try to verify this algebraically, and later on we will try to interpret this in an intuitive fashion of what this condition is actually trying to tell us. Okay, so first let's algebraically verify whether these relationships are true or not. Okay, so first let's choose the case that sigma is 1 and tau is, let's say, 2, right? So what is the image of f sub 1? Can one of you tell me what is the image of f sub 1? Please volunteer. What is image of f sub 1?
It's just a singleton 5.
It's just the singleton 5. Okay, and what about image of f sub 2? What is it?
Singleton 10.
Very good. Okay, so this is the the image of f sub 1 and image of f sub 2. Now if you take their intersection, because this is 5 and this is 10, right? I hope you agree that if you intersect them you get the empty set, right? On the other hand, if you look at f of 1 sub 1 intersection 2, right? So for this you have to take the set 1, intersect it with 2. So I hope you agree that there is nothing common between these two sets, right? So consequently, the intersection will be the empty set, right? And we will sort of trivially assume, right, that the image of the empty set is empty, right? So so notice that empty set, okay, I mean if you sort of have to go beyond go by the definition that we gave above, so the empty set will be a function that will go from x minus 1 to r, right? And we will imagine this x minus 1 to be the empty set, right? And consequently the image will also be empty. Okay, so this follows by some assumptions that we will separately make. Consequently, the image of this f of this empty set will be empty, and accordingly you can see that this intersection and image of f of this intersection is one and the same, right? Similarly, let's look at the case where sigma is made up of the singleton 5 and sorry, sigma is made up of the singleton element 1, and let's say tau is made up of these two elements 1 comma 2, right? So let's try to again ask what is image of f sub 1, as we discussed before that this is 5, and what about image of f of 1 2, which is tau over here? Can one of you volunteer and tell me what should this be? What is this image of f of 1 2? So recall this is the function, right? So what do you think image of f12 should be? Yes, Ichit, please go ahead. Please unmute.
Hello.
Yeah, I can hear you. Go ahead.
Yes, sir. All the points on the real line between 5 and 10 comes under this.
So I hope you agree that this is this interval, closed interval
Yes,
5
sir.
to 10. Is
Yes,
this okay? Okay, thank you
yes,
very
sir.
much. Okay, so this is indeed the image. So now if you look at the intersection of image of F1 intersection image of F12, I hope you agree that this will just be the singleton 5 because you are taking this set and you are taking this set and you are intersecting them. So I hope you agree that you will end up with 5. And on the other hand, if you take image of 1 intersection 1, 2, right? So if you take this, then I hope you agree that the intersection of 1 and 1, 2 is precisely f of 1 and the image of f of 1 is again 5. So you can see that this these two things also match. Is this okay? So indeed one can conclude that this relationship over here holds true. Okay, so let me pause here for a second or two. If there are any questions with regards to how we manage to show these two intersections are, these two sets are one and the same, please let me know. This would be a good time to discuss that. Okay. Yes, Harshul. Yeah.
Yeah, so basically I had a doubt in the definition of the geometric realization. So we require two conditions: if sigma is injective and the image f sigma intersection f image f tau is a image of f sigma intersection tau. So the second condition that I understand is because we want that the collection to be a subset topology. That will help us ensure that intersection remains still
I mean, I'll
remains
talk about why
topology.
we require these conditions. Is this
Yeah,
okay?
so the first one, I had the doubt in the first one, like, is it required because of the topology or is it because we just want to capture the maximum information that we can from a simplicial complex?
So I will talk about that. See, the short answer is that, so recall what we are doing. We are taking this abstract simplicial complex. To begin with, it's just a collection of sets. Is this okay? Right?
Yeah.
And we want to define some, like in the subsequent course, that is in the lectures that will follow, we want to define something called as the homology of this set. Is this okay? Right?
I see.
Do you agree? So delta
Yeah.
is a collection of sets. To begin with, it's just a collection of sets. Like, what does homology even mean? What does the shape of a set collection of sets even mean? Is this okay? Do you agree?
Yeah.
Right? So what does it mean? So what we are doing is that when I'm actually talking about the homology of this abstract simplicial complex, implicitly I'm talking about the homology of a topological space. Which topological space? Well, it's geometric realization. Is this okay? Now,
Yeah.
the geometric realization is something concrete, right? It is something we can draw. Is this okay? Or at least we can imagine. So when I say draw, I mean, it has to be taken with a pinch of salt because anything that is higher than 3 dimensions, you cannot draw. Okay. So when I say draw it, there is some formal way of describing how it will look like in whichever dimension we want to imagine it in. And for that, it has a shape. Right, and we can talk about the homology or the shape of that geometric realization. Do you agree?
Yes.
Right, and whatever recipe I'm prescribing, I'm ensuring that the way we will talk about the homology of this abstract simplicial complex, that will correspond to the homology of this geometric realization. Does that make sense?
Yeah, that's why we require f sigma to be injected, so we have that correspondence. Yeah.
That's precisely the case. Is this okay? So if you, to others, those who did not understand, the answer is that I am going to, later on talk about homology of an abstract simplicial complex. In particular, I mean shape of this abstract simplicial complex. Okay, so when I talk about shape, the first thing that should arise in your mind is, oh, there is just a bunch of subsets that have been given to me. How can I even talk about the shape? Well, the answer is that I can talk about its shape when I view it in a certain fashion. And that certain fashion is what is this geometric realization. So I'm telling you how to view it. And the geometric realization is something that is concrete, right? It's not a bunch of just sets and so on. It's something that is concrete, that is something geometric in nature, and we can talk about its shape. So whatever is its shape, we want to sort of say that is the shape of this abstract simplicial complex. Okay, so that's roughly what should I say, the overall goal that we are trying to accomplish. Is this okay?
Yeah.
Okay, thank you. Welcome. Are there any more questions? All right. Okay, so I don't see any raised hands, so let us advance. Okay, so we can see that indeed for this f that we chose, okay, we indeed saw that the two conditions were satisfied, that is all these f sigmas turned out to be injective, right? And we also saw that f sigma intersection f tau, okay, sorry, image of f sigma intersection f tau, right? Image of f sigma intersection image of f tau. Okay, this turned out to be image of f sigma intersection tau. So these conditions indeed turned out to be true. And now let us draw the geometric realization. Okay, so what is the geometric realization of delta? This is the union of image of f sigma sigma in delta. So this is all I have to draw now, right? So I have these three functions f1, f2, f12, right? These are the three functions that I have. So the image of f1 is this, the singleton set 5. This is the singleton set consisting of 10, and the image of f12 is this closed interval 5, 10. Right? So I have to take their union, and I hope you agree that I will end up with something like this. Well, this is the geometric realization of the simplicial complex delta 1, 2, 1, 2. Okay, so I would like to correct my language a bit. I said this is the geometric realization. That is not correct. What I should have said is this is a geometric realization. Okay, so the geometric realization is not unique. Okay, there are thousands, or I mean, there are like infinitely many ways of coming up with a geometric realization of a given simplicial complex. This is just one such realization, right? So I hope you agree that this matches with the intuition that we had, that this simplicial complex, we should draw it in this fashion. Right now, I think if I'm not wrong, it was Pankaj who asked me why did we choose R. Well, that was just for convenience. We could have also chosen a map from F from V to R2, as long as the mapping maps these two vertices, that is 1 and 2, to two different points in R2, right? So let's say some vertex. So let's say this is your R2, and let's say this is some vector, this is some vector over here, and let's say you look at the union of these two vertices as well as this line segment that connects these two vertices over here, right? So this also can be viewed as a geometric realization of this simplicial complex. So in this way, you can see that this R was just a choice that we made for convenience, but we could have as well chosen R2 over here, R3 over here, any R raised to n that we would have liked, right? And as long as we mapped this 1 and 2 to two different elements in this Rn, we would have got the a geometric realization that has a similar what should I say, characteristic, that it looks like two vertices, right? And along with that, it's a line segment that is joining these two vertices. Is this okay? So let me pause here for a second or two. If there are any questions with regards to how did we come up with this geometric realization? See, the eventual drawing may look very, very simple. Okay, but the recipe is what I want to make sure you understood, how we adopted the recipe and came up with that geometric realization, right? So one can now ask, let's say if I give you a geometric realization, let's say something like 1, 2, 3, okay, and let's say 1, 2, 1, 3, and 2, 3. Is this okay? So now I ask you, I mean, this is an exercise for you. So let's say, I hope you agree that V is made up of 1, 2, 3. Do you think something like this will ever give us a geometric realization? Is this okay? Will something like this ever give us a geometric realization? Notice that on the right, we just have R. And so I encourage you to think whether, howsoever you construct this function, would you end up with a geometric realization? So when I say would you end up with a geometric realization, the question is basically you have to look at this F1, F2, F3, F12, F13, F23, and check whether each of these functions are injective, and whether this intersection property that we mentioned, that is something like this, whether this property is also satisfied for all possible choices of sigma and tau. Right. So if such a condition is satisfied, then indeed this function induces a proper geometric realization. However, if this property is, even if one of the property is not satisfied, then one can conclude that this function cannot be used to come up with a geometric realization for a simplicial complex. Okay, so this is an exercise. So let's say I give you a simplicial complex made up of these 6 faces, right? And let's say I ask you that f should only take v to r, right? So this is very specific over here. However you come up with this f, do you think this f will induce or help us come up with a geometric realization for this delta? Okay, so this is an exercise, but now let's go back to another example and see a case where the f doesn't is not correct, or one of the conditions is violated, and consequently this f does not help us come up with a geometric realization. Okay, so as before, the delta for us again is 1 2 1 2, right? And let's say we pick this function f, right? And this again goes from v to r. However, this time what I do is, for both 1 and 2, which are the two vertices over here, right? For both 1 and 2, I assign the value 5, right? So in the earlier case, I assigned 2 different values for f1 and f2, but this time I assigned the same value 5, right? So now let's see whether this f will give us a proper geometric realization, right? So again, let's see what happens. So f1 will go from x0 to r. X0 only consists of the element 1. So f1 of 1 will be 5. Similarly, f2 will go from x0 to r. Again, this consists of only one element, which is 1. So f2 of 1 will again be 5, right? So unlike in the earlier case where it was 10, the reason is that it is 1 into f of 2, right? So since f of 2 is 5 over here, this value also turns out to be 5. Okay, so that is something you have to keep in mind. Right, so let's do a quick check. Is f1 injective? Well, the answer is yes. Is f2 injective? Well, the answer is yes. Now let's see what happens for f12, right? So f12 has to go from x1 to r, right? So f12 has to go from x1 to r. Now what does this mean? It means that just 1 minute, I need to connect battery to I need to connect the charger to my laptop. All right. Okay, so what is F12? F12 goes from x1 to r. So what is x1? X1 is the collection of lambda 0, lambda 1 such that lambda 0 and lambda 1 lie in 0, 1, and lambda 0 plus lambda 1 is 1. Right. So now with this in mind, what is lambda 0, lambda 1 map to, under this F12 map? Well, F12 of lambda 0, lambda 1 is lambda 0 of f of 1. Sorry, there is a typo here. And lambda 1 of f of 2. Okay, so this is what is the map. Now f of 1 is 5. F of 2 is also 5. So I can take this common and I'll be left with lambda 0 plus lambda 1. And since lambda 0 plus lambda 1 is 1, I hope you agree that I would end up with 5 over here. So notice that this doesn't depend on lambda 0 and lambda 1, right? That is the key thing, which means that F12, right? F12 maps the whole of x1 to just this set 5 over here. So now if I ask you whether F12 is injective, so clearly it is not, because all the points in x1 get mapped to 5, right? So it's clearly a many-to-one function, and consequently F12 is not injective, right? So since it's not injective, right, whatever realization we get using these F1, F2, F12, that will not be a valid geometric realization. But nevertheless, let's try to imagine what will happen. So this is image of F sigma. You take its union sigma in delta, right? So this is what the resultant geometric realization would be. Now image of f sigma is f1 is 5, image of f2 is 5, image of f12 is also 5. So what we are saying is that this delta that was given to us consists of these faces, and what we are saying is that I'll just try to imagine this as a single element 5, right? So what this discussion tells us is that you cannot imagine this as a single element 5, or you cannot imagine this as a single vector in any space. Okay, so that's what it is trying to tell us, right? And by sort of doing some trial and error, you will be able to figure out what other geometric realizations are not valid. Is this okay? So let me pause here for a couple of seconds. If there are any questions with regards to this concept of geometric realization, I'd be happy to explain. Let me know if you have any questions with regards to geometric realization. Okay, so again, I would like to re-emphasize why are those complicated looking conditions are put in place? Well, those are put in place to ensure, as I said, whatever geometric realization you end up with, its homology or its shape. Okay, so at this point, most of you may not know what homology means and so on and so forth, but nevertheless, whatever is the shape or the homology of that resulting geometric realization, okay, that homology is what we will be associating with the abstract simplicial complex. So whenever I tell you I'm talking about the homology of an abstract simplicial complex, implicitly I am saying that we will imagine this as a geometric object in this fashion, that is this geometric realization fashion, and whatever is the actual shape of that shape I will associate to the abstract simplicial complex. Okay, so that's what I'm doing. At this point, it will not clear, what is the shape of this abstract simplicial complex, what is the shape of this geometric realization. All those things we will learn in due course. But at this point, you need to understand what this geometric realization is all about. Is this okay? So again, let me pause for a couple of seconds. If you have any questions, I'd be happy to answer them. Okay, so at this point, if I give you any simplicial complex, you should be able to come up with its geometric realization. Okay, so that is something that you should be familiar at this point. Okay, and I will give you a bunch of exercises either during class or during as part of your assignments. Okay, so that you get a chance to learn a bit more about this geometric realization. And whenever we meet next, I'm more than happy if you ask me questions then as well. All right. Okay, so this is what this concept of geometric realization is all about. And we will now move on to the second half of today's class. Okay, so now we want to begin the study of homology. Okay, however, a study of homology requires some basic knowledge of some fundamental concepts of from algebra. Is this okay? Now, what we are going to study, okay, is actually part of algebraic topology, right? This needs to be emphasized, right? So most of the tools that we will be sort of be using to study topology will be algebraic in nature. Okay, so at this point, it will not become clear why do I say algebraic and what do I mean by algebraic and so on and so forth. However, when we actually study these tools, it will become clear to you that, oh, indeed, these are quite algebraic in nature. Okay, the other forms of topology, for example, are differential topology and so on and so forth. Right, so here we use a different set of tools to study the topology of a space. Right, whereas here we use tools that are mainly algebraic in nature. All right. Okay, so before we sort of embark upon understanding what are the different tools that we'll be using to study topology, in particular homology, okay, we need to understand some fundamental concepts from algebra, and that is what will be the focus for the rest of this class. Okay, so I'll sort of be slightly quick because these are things that I'm sure most of you must have already studied, and if not, I had also covered them in the linear algebra class. Right, so this is not new, but this will more be like a revision. Okay, so the first of the things that we will be studying is that of a group, right? In particular, we will be studying what is an abelian group, right? So what is an abelian group? Whenever I say an abelian group, what should pop in your mind is a pair, right? So the pair is made up of a set along with an operation, right? So G over here is some set, and this star over here is a binary operation. So binary operation means that it is a function. Okay, and since it's binary, it means that you have to give two elements from G to it, right? So you give me two elements from G to this operation, and it will spit out an element in G again. So this is very, very crucial. So this operation takes as input something from G, another input from G. So you takes these two inputs, combines them, or does some operation on these two inputs and spits out another element in G. So that is very, very important. And this operation over here needs to satisfy these axioms. Okay, so the first is that the first of this is called the associativity property. So the associativity property, okay, tells us that such a relationship hold. Okay, so of course, when I write it, it may appear very, very trivial. Okay, but let's try to understand what this condition means. Okay, so notice that this is a binary operation, right? So what will happen if I want to use this operation and or perform this operation over three elements, right? So clearly this operation can only be performed two at a time, because by definition this operation can only take two inputs from G and spit out an input in G, spit out an output in G, right? So whenever I'm given three elements, the first question that may arise is, should I first perform the operation between A and B? Whatever is the output, should I take that output and perform the operation with C? Or alternatively, should I first perform the operation between B and C, and whatever is the output and A, you perform the operation between the resultant and A? Okay, and you may end up with some result over here, and you may end up with some element in G. The associativity property says that however you perform the operation, the resultant in G would be the same. And consequently, okay, I don't have to worry in which way I'm performing the operation. I can simply write this as ABC. So this can be used to interpret either this way of performing the operation or this way of performing the operation. Is this okay? So whenever such a relationship actually holds true, we will say that the binary operation is actually having the associativity property. The next property is that of the identity element, right? So this means that there is some designated element in G such that this condition actually holds, right? So for every element A in G, if you perform the operation between E and A, or if you perform the operation between A and E, right, the resultant should be A itself, right? So the identity means that if you perform, if you take this identity element and combine it or use this to perform the operation with any other element, the identity element sort of leaves the original element unchanged. So you can see that A and E is when you take this as give this two elements as input to the binary operation, the output is A. So this input remains unchanged. Okay, so that's the meaning of identity, right? And this relationship should hold for all A in G. And the next property is that of an inverse element. This means that for every A in G, there must exist some B in G such that A times B or B times A, whatever, however you perform the operation, this must be the identity element itself, right? And typically, we will denote this inverse element either by minus A or A raised to minus 1, depending on whether we are viewing this operation as either being additive in nature or multiplicative in nature, right? So if it is additive in nature, we will denote the inverse as minus A, and if the operation is multiplicative in nature, we will indicate it by A raised to minus 1. And the last property is that of commutativity, which basically says that it doesn't matter the order in which I perform the operation, right? Either I give A as the first input or B as the second input, or vice versa. However you perform the operation, the result should be the same, right? So see, when I was a student, okay, this is something I told during my linear algebra class itself, but nevertheless, let me say this again for those who may be being part of this such a discussion for the first time, right? So when I was in my undergrad or during my PhD, okay, when I first learned algebra, I found it a very dry topic. I was like wondering, oh, this is some bunch of rules, and as long as these rules are satisfied, okay, it's a group. I used to like always wonder, oh, so what? I mean, who cares, and so on and so forth. But over a period of time, I've started appreciating algebra a lot. Okay, and I realized that the reason I started appreciating algebra a lot was because somebody taught me algebra in the right way. Okay, so right in the sense, of course, from my perspective. So what is that right, or what is the way that I really liked? Okay, so why do we study this group? Okay, the reason is that let's look at a bunch of examples that are groups, right? So here are a bunch of examples, right? The set of integers along with the usual addition operation, right? So the set of integers with the usual addition operation, or the set of rational numbers with the usual addition operation, the set of real numbers with the usual addition operation, the set of vectors in Rn with the usual addition operation, or the set of rational numbers. You remove the zero element and look at the rest of the elements with the usual multiplication operation, right? So this, and finally, if you look at Zn with the addition modulo n, right? So Zn over here is a set that includes 0, 1 all the way up till n minus 1, and the operation that you define is the addition mod n, right? So all these things by themselves are different entities, right? So here the set is different, here the set is different. While the operations are the same, the sets are different. Here also the set is different. Here this is a higher dimensional space. Here the operation itself is different. Here again the operation is different. Nevertheless, right, all of these are groups, right? So instead of trying to prove a property separately for this, separately for this, separately for this, and so on, what I have defined is, I have defined an abstract concept called as a group, right? So group is abstract because by itself it has no meaning, right? However, I should say it has no physical meaning. However, I know that this is a group, this is a group, this is a group, this is a group. So instead of trying to prove properties separately for these individual, concepts over here, or individual objects over here, what I do is I extract out the common properties, combine them, and define something called as a group. I prove a property for a group, and in one shot, I know that that property will hold true for this, the property will hold true for this, the property will hold true for this, and so on, right? So that's the beauty of algebra in particular, the beauty of some algebraic concepts, that in one shot, I'm able to prove some property for a wide class of objects. Is this okay? So that's the reason why working with algebra is really beneficial. All right. Okay. So there is a remark that I wanted to make. Okay, so typically when we will be dealing with groups with additive nature, okay, we will denote the identity element simply by 0, right? So even if it is like Rn plus, I will denote the identity element simply by 0, and depending on the context, you should interpret this 0 to either mean this vector of all zeros or something else, right? Okay, so let me pause here for a second or two. If there are any questions with regards to this definition or a concept of a group, this may be a good place to ask. Do you have any questions? All right, I don't see any raised hands, so maybe I advance. Okay, so the next concept that we will need throughout this course is that of a field, right? So what is a field, right? So field, like a group, is some abstract object, right? However, unlike a group, for a field there are two operations. Okay, so these operations we denote as plus and multiplication, right? However, this could be arbitrary operations, and we just require that these two operations satisfy some of the properties. So again, what are these operations? Well, these operations, again, you have to give two elements from F as input, and the output will be another element in F. And similarly, for the multiplication operation, you have to give two elements from F, and the output should be in F again, right? So field you can think of as generalizes the properties of the usual addition and multiplication on R. Okay, so the real line is the archetypical example of a field, right? But instead of focusing too much on R, what we try to do is we try to look at the properties of addition and multiplication on R, extract it out, define this, this abstract object over here, okay, and study the properties of this abstract object, and whatever properties hold true for this object over here, they will automatically hold true for the real line and any other field in general. Okay, so what are the properties that this addition and multiplication operation needs to satisfy? The first is that we require that if you look at just f along with this plus operation, these two things together must form an abelian group. Separately, if you take this f, remove the identity from this set, the additive identity from this set, right? Remove it and look at the rest along with the multiplication operation, then this must also be a separate abelian group. So this itself must be an abelian group. This also must be an abelian group. And separately, we require that this multiplication distributes over plus. So which means that if I take a plus b, multiply it with c, then this must equal this operation on the right. Okay, so let me emphasize what is happening on the left. Because of the presence of brackets, what we are doing on the left is that we are first performing the addition operation, and thereafter whatever is the result, this will be an element in f. Whatever is the output, you take that output and multiply it with c. And on the right, what we are doing is we are first performing the multiplication operation. So these two individual multiplication operations we are performing, and whatever is the resultants, we will sort of add them up, and this property states that however you perform the operation, the result must be one and the same. Is this okay? So you can see that examples of fields include R plus dot, Q plus dot. So this is the set of rational numbers with the usual addition multiplication, the set of complex numbers with the usual addition and the standard multiplication operation in complex numbers, right? And so these are examples of fields, and here is an example which is not a field, right? So this is the set of integers with plus and scalar multiplication, and one can see that this is not a field, okay, because z, if you even remove the additive identity and look at the multiplication, okay, so this is not an abelian group. So can one of you volunteer and tell me why is this not an abelian group? Why is this not an abelian group? Would one of you like to volunteer and tell me why this is not an abelian group? Yes, Pankaj?
I think the inverses doesn't exist.
Very good, right? So like, for example, if I give you 2, I know that in this case, the multiplicative identity is 1, right? So, from the study of rational numbers, I know that only when I multiply 2 with half would I end up with 1, but this does not belong to the set of integers, right? So that's why the the multiplicative inverses do not exist, and that's why this is not an abelian group, and consequently this is not a field. Okay, and the last concept that we will be discussing today is that of a vector space, right? So again, like groups and fields, vector spaces are also abstract concepts, right? In order to define a vector space, I need 4 things. One is a set V, other is a field F, and these two operations, right? So notice that although I write it as plus and dot, okay, you have to interpret what this plus and dot mean, right? So field itself will come with its own plus and multiplication operation, right? So a field itself will come along with a plus and multiplication operation. So this plus and this multiplication are different to this plus and this multiplication in general. Is this okay? So so one has to be careful, right? So to define a vector space, we need these 4 objects over here. One is the set, the field F, which will come with its own addition and multiplication operation, then a separate addition and a separate scalar multiplication operation. Okay, and this scalar, this addition is as we had the description in the context of a field or a group, right? So the input should be two elements from V, right? And the output will be an element in V itself. However, for this dot, notice that the description is slightly different. Okay, so the input should be something from the field, right? And the second input should be something from the vector space, that is V over here, the set V, and the output will be in V itself, right? And if this addition and scalar multiplication satisfy the following four properties, that is V along with plus should form an abelian group, right? And in addition, the scalar multiplication operation satisfies the following properties, that is 1 dot V. So notice that 1 over here represents the multiplicative identity of the field. Okay, multiplicative identity of the field. Okay, so 1 dot V should equal V for all V in V, right? So if such a condition holds, then we require that such a condition hold for this scalar multiplication operation. Similarly, we require that this compatibility property also holds. So compatibility means that, so notice that here there are two dots that are here. So this dot over here is the multiplication in the field, right? So this is the multiplication in the field, whereas this is the multiplication or the scalar multiplication operation defined in the context of the vector space, right? So what we are saying is that in the left, we first perform this operation between two elements of the field. Whatever is the result, you take its scalar multiplication with an element of the vector space V. Whereas on the right, what we do is we take this element from the field, perform the scalar multiplication. Whatever is the output, you take another element A from the field, perform the scalar multiplication with the element in V. So notice that here there are two scalar multiplications, whereas here you have a multiplication from the field and here you have the scalar multiplication. So this compatibility means that however you perform the operation, the result should be the same. And the last property is that of distributivity. That is A dot U plus V must satisfy this condition. Again, this is the scalar multiplication and this is the addition in the vector space, right? And this is the scalar multiplication, this is the scalar multiplication, and this is the addition in the vector space. Whereas over here, notice that the addition is in the field, right? So this is an element of the field, this is an element of the field. So this addition is the addition in the field, and whatever is the resulting element in the field, I have to take that element and perform the scalar multiplication with this element of the vector space. And on the right, you perform scalar multiplication, and this addition over here is the addition in the vector space, right? So one of you may ask, why did I not use a separate notation for this addition over here and this addition over here, right? So ideally I should have used separate notations. However, on one hand it may help because it will help us keep the two cases distinct. However, having these complicated notations will unnecessarily complicate the discussion, and that's why often mathematicians prefer to be lazy and leave it to the reader to understand from the context whether this addition is the vector space operation or this is the field operation. So here it is the field operation, whereas here it's the vector space operation. And you can see that there is, while mathematicians try to be lazy or sloppy, okay, they always try to ensure that the reader is able to unambiguously interpret what is written over here. So this addition cannot be vector space addition because these elements are from the field, right? And similarly, this cannot be field addition because these are elements from the vector space. Is this okay? So, and again, we will henceforth continue to be sloppy in the sense that instead of writing a vector space using a field addition, scalar multiplication operation, we will simply write it as V and, implicitly say that, okay, there is an underlying field, there is an underlying addition operation, and there is an underlying scalar multiplication operation. So from the context, it will be clear what a vector space is. I mean, what are the operations that we are talking about. Okay, one more thing, henceforth, whenever we have a vector space, we will refer to the elements of this vector space as vectors. Okay, whenever I say vectors, you don't have to interpret it as some element of Rn. Okay, you don't have to do that. You can just think of this as some element of V itself. Okay, so there are a bunch of examples. Okay, I encourage you to sort of look at them on your own, and if you have any questions, you can ask me next time as well. Okay, so with this, I'll stop, and in the next class, we will talk about homomorphism, isomorphism between groups, vector spaces, and things like that. Okay, so with this, let me stop the recording. I'll be available for a few more minutes. If you have any questions, you are more than welcome to ask them.